These days, it's actually pretty hard to find a motherboard repair that's not just successful, but also fun to watch. Uploading a video where I replace one tiny resistor in a minute doesn't really feel worth it, and repairs that are truly interesting for most viewers don't happen that often. So today I want to share a repair that took me several days and turned out to be way more interesting than I expected. Along the way, I ran into a lot of unusual problems and some pretty cool moments that are worth talking about. This repair is definitely not a typical one. I think many of you will find it interesting, and by the end you'll see how this repair actually ends up. So get comfortable at your desk or on your couch with your phone or TV, grab a cup of hot tea and let's dive in. Please welcome the GIGABYTE B550 AORUS Elite AX version 2. This is one of the most common motherboards on my bench, not just because it's relatively inexpensive and often faulty, but because it's a very popular aim-for board with DDR4 memory, which makes it especially relevant during the current memory shortage. I received this motherboard with a very common issue description: does not power on. Having repaired dozens of these boards before, I initially thought this would be a quick fix. I already knew which areas to check for typical problems, and at first glance the board looked quite promising. However, the more time I spent inspecting it, the clearer it became that the issue was far from obvious. The first thing I usually do is measure the resistance of the main power rails. 3.3 volts. We have 422 ohms, looks normal. 5 volts, kilo ohms. 12 volts, also kilo ohms. Minus 12, nothing. It's normal. 5 ESB, 133 kilo ohms. Okay, what coils we have? Right here, this is a memory power line, 5.2 kilo ohms. This is probably PCH, 900 ohms, normal. Another one, even mega ohms. Also, let's measure the CPU. CPU, we have mega ohms, CPU 2V core. 150 mega ohms, and V core itself, even kilo ohms. Okay, nice. So the resistances are normal, as usual. Let's try to power it on to see if there is a reaction to a power button. We're going to use, as usual, it's Ryzen 3200G. Okay, power on. So 120 milliamps. This is normal. Pressing power button, and nothing happens. Let's measure if we have 3 or 5 volts on the button. And this is the pin number 3 here. And we have 5 volts. Okay, so the button is working. Okay, let's remove heatsinks and make an inspection right here. Since the resistances are normal but the board does not react to the power button, the next step is to remove all the heatsinks and inspect the components hidden underneath. Even when the main power rail resistance looks fine, it's quite common to find a short on a control rail or a local power line. It was a bit surprising to see the PCA chipset with a fresh, intact thermal pad between the heatsink and the chip. Still, the heatsink has to come off so we can check the chipset itself for any visible issues. Okay, since we don't have any reaction to the power button, we need to first check if the SIO gets power. It should be 3 VSB. This should be a pin number 95. This is the second pin from the right side. Here's our SIO. And we need a pin number 2 from the right side of the bottom. Let's measure the voltage. And we have 3.3 volts. 5 volts and 3.3 volts standby power were present, so I followed the typical aim for power-up sequence. When we press the power button signal is pulled to ground. This is an active low signal. That signal goes to the SIO chip, and if the SIO is properly powered, it forwards the signal to the CPU. This signal is called PS out, and it is also active low. If the CPU is properly powered, it then releases the sleep signals, which tells most of the motherboard to wake up and transition from the S5 state, which is a deep sleep or power off, to the S0 state, which is a normal operation. At that point, once the SIO gets the sleep S3 signal from the CPU, it can finally tell the power supply to turn on. This is a very simplified sequence, and on this particular model the SIO receives that signal indirectly through a separate power controller. So the next step is to measure the sleep S3 signal on the CPU side to see whether the CPU is actually releasing the sleep states or not. Okay, let's measure the RSM-RST which goes from the CPU. There's here. Okay, we have RSM-RST. So pressing the button does nothing. Here we should have a SLPS3 up and running right here. And we don't have it, it's just 0.5 volts. As you can see, we only have a half of a volt here, which is far from the expected 3.3 volts. That tells us the CPU is not releasing the sleep S3 signal, and that already narrows the fall down quite a bit. One possible reason for this is that the signal line is being pulled down externally, for example, by a shorted capacitor or resistor. This is easy to check by measuring the resistance on the line. In this case, the resistance is in the kiloohms range, so we can rule that out. The other, and at this point the only remaining possibility, is that the CPU is not being powered correctly. That would mean one or more of the CPU standby power rails are missing. On this motherboard, there's two main standby rails, VDDP S5 and VDD18 S5, 0.9 volts and 1.8 volts accordingly. Both of these rails are generated using linear regulators. The lower one provides the 0.9 volts rails, and the upper one is responsible for the 1.8 volt rail. That's why it was quite a surprise to see that the supposed 1.8 volts rail was actually sitting at 3.3 volts. What makes it even worse is that this rail goes directly to the CPU, which means an overvoltage situation and a real risk of damaging it. Sometimes things go badly, but not this time. I tested the CPU in a known good motherboard and it turned out to be perfectly fine. Okay, so I guess maybe I found a problem. So what do you see here? This is two low dropout linear regulators, EM5109. Those regulators, they have a supplying power and supplying voltage of 3.3 volts on these pins. These pins are enable pins, so they have enabled 1 and we have enabled on the first regulator. And so it is designed, the regulator number 2 to provide VDDP S5, and we can see this 0.9 volts. This is V out, and this regulator should provide 1.8 volts VDD18 S5, and we have here magically 3.3 volts. Moreover, these regulators have 0.8 volts of reference voltage, which you can see on this pin, and this is correct, and on this pin, this is 0. So let's replace it. Here I should know that I didn't have an AM5109 regulator in stock, but I did have a 5103 which has the same pinout and very similar characteristics, so it was a suitable replacement. My first thought was that the linear regulator itself has failed internally, allowing the 3.3 volts input to pass straight through to the output. So I replaced it with a known good regulator from another board, and to my surprise, the output was still 3.3 volts. At that point, the only remaining suspect was the regulator's feedback circuit, which is formed by a voltage divider made up of two resistors. Those resistors' values are carefully chosen so that the regulator adjusts its output to reach the internal reference voltage, in this case 0.8 volts. I decided to desolder those resistors and measure them directly, and during the desoldering process with hot air, one of the resistors cracked into two pieces. That confirmed it had already been damaged, even though the crack wasn't visible before, not even under the microscope. I also decided to solder the original regulator back in place, since by that point it was clear that the regulator itself wasn't the problem. After soldering in the new resistors, the power rail was restored and now showed the correct voltage of 1.8 volts. The feedback pin also measured the expected 0.8 volts. Okay, so we have restored normal 1.8 volts rail, soldered new resistors for voltage divider. Let's see if we have any changes. Pressing power button. And finally we have a reaction. Okay, do we have any capture? I guess no, because we have a steady 2.2 amps. So there's a problem somewhere else. Let's try to reflash the BIOS with the new firmware and let's see if it helps. The motherboard now started to react to the power button, and I was happy to see this. However, the board still did not give a pause screen. The board appeared to be stuck somewhere in the later stages of the power-up sequence, possibly during data exchange over the VAD protocol. I decided to reflash the BIOS with the latest firmware version, since this behavior looked like the board might be hanging during BIOS access. After reflashing the bias and soldering the chip back in place, I tested the board again, but the board was still stuck. I decided to check SPI channel to the bias chip. Okay, so we're trying to do clock here. Let's see. And clock is present, so we see that there is a clock signal going on and out. And that's it. Okay, fair enough. Then we would like to see the data output. Here we have a data output pin. Let's see. And you see that we have a data output as well. So the bias is actually output the data. Let's see the data in. Okay. And pin number 2. So we have a data in as well. Nothing changed, so I followed to checking the PWM signal on the V core and SOC phases within oscilloscope. At this point, the remaining possible issues are a cracked solder joint out of the CPU socket, a fault inside the PCH, or a problem within the PWM controller's VID data lines caused by internal damage. Blindly replacing the PCH or the PWM controller just to see if something changes didn't seem reasonable to me. At this point, I decided to set this board aside. I've already spent a lot of time on it. It's possible that after some time, a fresh look might give me a new idea about why it still doesn't post. Not every repair ends in success, but this one was genuinely interesting and very productive. I ran into something I've never seen before, resistor cracking during a hot air desoldering, even though it looks perfectly fine under the microscope. If you have any ideas about what could still be causing this issue, feel free to leave a comment below. I read all of them, and your input is always appreciated. Please let me know if you'd like to see unsuccessful repairs like this alongside the successful ones. Your thoughts and feedback are greatly appreciated. Thanks for watching, and I'll see you in the next repair.